Hello, guys. Good morning, everyone. So, today I am here with another new chapter of physics, atoms. Okay. So, as you guys know me, I'm Sumit Nahak. I had secured All India rank 691 in NEET and currently pursuing MBBS in AIIMS Bhubaneswar. Okay. So, let's begin the session today. So, before beginning the chapter atoms, I would like to say this is one of the most important topics from modern physics. Okay, in modern physics you have three chapters: atoms, dual nature of matter, and nuclei. And every year from modern physics at least you'll get 6 or 7 questions from modern physics. And modern physics is such a easy chapter, with a very little number of with a very less number of formulae, and has a very high weightage. Okay, so it plays, so that is why this is one of the most important topics in your physics. Okay, so let's begin. So I'm beginning with the question number one. Question number one says, in a Rutherford scattering experiment, when a projectile of charge Z1 and mass M1 approaches a target nucleus of charge Z2 and mass M2, whatever they are asking you in question, first you try to draw that in your paper. Try to draw the diagram, then it will be very easy for you to solve the question. Okay, so I'm making a diagram for this. This is a Rutherford experiment. Rutherford's gold foil experiment. Okay, it's a gold foil. What he did, when a projectile of charge Z1, this is a projectile which has a charge of Z1 and mass of M1. Okay, and it is approaching a target nucleus. This is the target nucleus. This is the target nucleus which has a charge of Z2 and mass M2. Okay, and the distance of the closest approach, it started approaching this atom. Okay, this is our target nucleus, and this is the projectile. Yeah, so projectile is approaching towards the target nucleus, and then what is saying, this was the initial stage. Finally, the closest distance between the target, this is the target, and this is our projectile. The closest distance between them was r naught. Okay, so we have to find out the energy of the projectile is directly proportional to what? Directly or inversely proportional to, if it is directly or inversely proportional to any one of the following options. Okay, so let's begin. So initially, as you can see here, it initially it has a kinetic energy. Initially, it only had kinetic energy. Kinetic energy of what? How much kinetic energy it had? Kinetic energy initially was half mv square. Okay, half mv square. And then at the final state, all the kinetic energy will be converted to potential energy. All the kinetic energy will be converted to potential energy. Okay, initially it only had kinetic energy. Okay, and when it approached to a distance of r naught, it will only have potential energy. So all the kinetic energy will be converted to potential energy. So what will be the potential energy here? As you know, the formula for potential energy is K Q1 Q2 upon R. What is R here? R naught. K, value of K, I don't think we need to write because in options they have not given anything related to K. So just write it as K. What will be the value of Q1? What will be the value of Q1? If it is saying it has a charge of Z1, Q1 is Z1 and Q2 is Z2. This has a charge of Z2. Okay, so both the charges also we have. So kinetic energy is now equal to K Z1 Z2 upon R naught. Can I write that? Can I write that? Yes, I can write. Why? Because all the kinetic energy is being converted to potential energy when it has approached to the target. Okay, so all the energy has been converted. That is why kinetic energy I'm writing is equal to potential energy. Okay, so now you have a formula for energy is equal to K Z1 Z2 upon R naught. So now it's now compare the options. The energy of the projectile is directly proportional to Z1, Z2. Energy is directly proportional to Z1, Z2. Yes, it is. Energy is directly proportional to Z1, Z2. So option A seems to be correct. But as I say always, check all the options, then you move to next question. Okay. So I'll check the option number B. Inversely proportional to Z1. No, it is not inversely proportional. Option C says, is it directly proportional to masses? No. Mass is not even related to this. Is it directly proportional to M1, M2? No. Mass is not related to this. So the answer is option number A. It is directly proportional to Z1 and Z2. I hope you understood the question. Okay. So with this, I'll move to question number 2. Question number 2 says the Bohr model of atoms. See, this is again one of the chapters where you have to go through NCERT lines. Huh? Because in many previous year questions, you will see they have asked questions directly from the NCERT lines. Okay, so it hardly contains 4 or 5 pages in NCERT physics if you see. So please go through those pages at least twice or thrice so that you will at least remember something out of that. You won't be blank. Okay, that's it. So moving on to question number 2, the Bohr model of atoms. I'll read out the options. Predicts the same emission spectra for all types of atoms. Option number B says it assumes that the angular momentum of electron is quantized. Option C says uses Einstein's photoelectric equation. And option D says predicts the continuous emission of spectra of atoms. So again, going with option A, does it predict the same emission spectra for all types of atoms? No. Different atom has different emission spectra. Okay, if you know those formulas, 1 by lambda is equal to r z square 1 upon n1 square minus 1 upon n2 square. If you know this formula, n1 n2, n1 n2 means the emission spectra. Okay, if a electron is moving from n1 to n2, it will emit some spectra. So it will differ from atom to atom because z is there. So z value is different for all the atoms. That is why you will have a different spectra. Different spectra means different lambda or different spectra. So option A is wrong. Going with option number B, option B. Option B says it assumes the angular momentum of electron. It assumes the angular momentum of electrons is quantized. Yes, angular momentum of atoms is quantized. It is nh upon 2 pi. It is quantized. So option number B is correct. Again, option number C, no, it doesn't make any sense. It uses Einstein's photoelectric equation. No, it does not. Option number D says it predicts the continuous emission spectra for atoms. Yeah, it does predict. Okay, so this was an easy theoretical question. I'll move to question number 3. Question number 3 says when a alpha particle of mass m, a alpha particle of mass m. Those who don't know what an alpha particle is, I'll like to say alpha particle is helium 2 plus atoms. Okay, these are helium 2 plus atoms, alpha particle. So Rutherford used helium 2 plus atom. He scattered alpha particles. Alpha means helium 2 plus atoms. Yeah. So alpha particle of mass m, which is moving with a velocity, of v. Alpha particle of mass m moving with a velocity of v. Okay, it bombards on a heavy nucleus of ZD. It bombards with a heavy nucleus of ZD. Its distance of closest approach from the nucleus. Yeah. Again, when it bombarded with this, the distance of closest approach, this r or r naught, whatever, will dependent on masses, which of the following. Okay, okay. So again, the way, look at the way I'm approaching to each question. Okay. So in the first question, what did I do? What did I do? Initially, it had only what? Kinetic energy. What was the kinetic energy? Half mv square. And finally, it will only have potential energy. How much potential energy it will have? How much it will have? K alpha particle ka charge. Charge of alpha particle 2e into Q2. Q2 is ZD upon R naught. Yeah? Are you getting me? Initially, it only had kinetic energy. And finally, when it is so close to the target nucleus, it will only have potential energy. So you write both the formula, kinetic energy, potential energy, and then you know what kinetic energy will be equal to potential energy, because all the kinetic energy is being converted to potential energy. So now I will equalize both of them. Half mv square is equal to k z e square 2 2k z e square upon r naught. Yeah. So the closest approach r naught will be equal to 4k z e square upon mv square. So this will be the formula. So R naught is proportional to reciprocal of mass. Mass is in the denominator. It will be proportional to reciprocal of mass. So you got your answer. Answer will be option number A. R naught is proportional to reciprocal of M. Yeah. So with this, I'll move to question number 4. Question number 4 says the ratio of kinetic energy to the total energy of an electron in a Bohr orbit of hydrogen is equal to what? If you remember, if you have attended the theory classes for this chapter atoms, you must be knowing that the kinetic energy is equal to negative of the total energy. Yeah, this you have to remember. This should be in your fingertips. Yeah, so that you need not think much about these questions. Just put the answer and move to the next question. Yeah, so kinetic energy is equal to negative of total energy. This is the formula. So they have asked you what is the ratio of kinetic energy to total energy. It will be what? -1 upon 1. 1 is to -1. Option number B. Okay. But if you want to understand the concept behind it, I would like to explain. See, you know that the potential energy of an electron in Bohr's orbit of an hydrogen atom is equal to potential energy. First, I'm talking about potential energy. Potential energy is minus k z e into e upon r. This is the potential energy. Kinetic energy is equal to k z e into e upon 2r. So the total energy will be equal to minus of k z square upon r plus k z square upon 2r. So total energy will be equal to minus k z square upon 2r. Okay. So this is from this only we got kinetic energy is equal to minus of total energy. As you can see, kinetic energy value. It is negative of total energy. Okay. I hope you understood this. So with this, I'll proceed to next question. Question number 5. Question number 5 says an hydrogen atom in ground state excited by a monochromatic radiation of lambda equal to 975 Armstrong. What is a ground state? What do you mean by ground state? Ground state means n equal to 1. Remember this. And then it was excited by a monochromatic radiation of lambda equal to 975 angstrom. It was excited by 975 angstrom. So the electron first it was in ground state, it will move to some one of the other state. Okay, first it was in n1. So from this orbit it will move to the next orbit. When you give a radiation of lambda equal to 975 angstrom. Okay, so the number of spectral lines in the resulting spectrum emitted will be what? So if you know the formula, 1 by lambda is equal to r z square into 1 by n1 ka square minus 1 upon n2 ka square. If you know this formula, see 1 by lambda 975 into 10 to the power, this will be a tough equation to solve. R z square, R is Rydberg's constant, R z value of z is 1, ground state is 1 square minus 1 upon n2 ka square. Okay, so you have to solve this will take a lot of time to solve. If I'll solve this will take a very long time to solve this equation. So you solve this. By solving this you'll get the value of n2 as 4. By solving this the value of n2 you'll get is 4. Okay, so what is happening here? When in the hydrogen atom a electron was present in the first cell n equal to 1, but when you emitted a wavelength of 975 angstrom, what happened was the electron from the cell number 1 it moved to the cell number of 4. It moved to cell number 4 because of the energy from 1 to 4. Okay, so they are asking you what will be the number of spectral lines in the resulting spectrum. For the number of spectral lines, you again have a formula. For the number of spectral lines, you again have a formula. What is the formula? N into n minus 1 upon 2. Okay, the value of n is 4 here because it is moving to the fourth cell. 4 into 4 minus 1 upon 2. 2, 2, it will be 6. So number of spectral lines emitted is 6. I hope you understood this. Okay, it excited from 1 to 4, cell number 1 to cell number 4. So that they were asking what are the number of cells, number of spectral lines emitted. The number of spectral lines emitted is 6. I hope it's very clear. So now I will move to question number 6. Question number 6 is an electron in hydrogen atom make a transition. An electron in hydrogen atom make a transition from n1 to n2. So this is our hydrogen atom. So if this is the cell number n1, this is the cell number n2. This is our hydrogen atom. Draw the diagram first. So an electron in hydrogen atom is making transition from here to here, n1 to n2, where n1 and n2 are principal quantum number of two states. Okay, so assuming the Bohr's model to be valid, the time period of the electron in the initial state is 8 times the fine that in the final. 8 times that in the final. So they are asking you what are the values possible for N1 and N2. I think options are has been omitted here. I have the question, so I'll write the options for you. They're asking you what are the possible values. What are the I'm writing the question here. What are the possible values for N1 and N2? Okay. Option A, option B, option C, option D. Possible values of N1 and N2. Which one of the following is correct? We have to choose. So this is the question. We have to solve this. Okay. This is the hydrogen atom. An electron made a transition from N1 to N2. We have to choose if the time period is 8 times. If the time period of the electron is 8 times of the final, initial state is 8 times that in the final. So you have to choose the correct answer. Yeah, from this 4 options. So what we know is time period is equal to what? 2 pi r upon v. Time period is equal to 2 pi r upon v. And another formula we know, this is how this became our equation number 1. Another formula we know that angular momentum is always quantized in Bohr's model. So if the angular momentum is quantized, what is the value of angular momentum? M V R L. L means angular momentum, which is equal to MVR, is equal to NH upon 2 pi. NH upon 2 pi. Okay, so from here, I can get the value of V. What is the value of V? NH upon 2 pi mr. This became our equation number 2. So now what I'll do, I have the value of V. I'll put the value of V in time period equation. Putting the value of putting the value of equation number 2 in equation number 1. Equation number 1. What was the equation number 1? 2 pi r upon V. 2 pi r upon V. So instead of V, I'll write NH upon 2 pi mr. 2 pi r upon NH upon 2 pi mr. So time period will be equal to 4 pi square m r square upon NH. Okay. Now we know R is directly proportional to n square upon Z. So it is proportional to n square. Okay. So since R is proportional to n square, time period will be proportional to what? Time period will be proportional to R square up. See, okay, this. I'll write the whole equation. Write R as R square is proportional to n square. So write R as kn square. R is equal to kn square. So time period will be equal to 4 pi square m into k square n to the power 4 by nh. Okay. So time period will be proportional to n ka power 3. Time period will be proportional to n power 3. Okay, now, so what is this? What it is saying? The initial time period is time period of the electron in the initial state is 8 times of the final. So what are the possible values of n? Ti upon Tf is equal to 8 is equal to Ni to the power cube upon Nf to the power cube. So Ni upon N5 becomes 2. So which of the following had which of the following, when you divide them, you get a value of 2 in these following options. You get a value of 2. You get a value of 2 only in the case of A. 4 upon 2 is 2. Okay. So option number A is correct. Did you understand what I did in this question? See, again, I'll explain you. They gave you an hydrogen atom and they told you in that hydrogen atom, electron made a transition from N1 to N2, N1 to N2. And they told you that the time period in the final state was 8 times of the initial. 8 times of the initial. Okay, and then what will be the possible values for N1 and N2? Then I did so many things and found out that time period is directly proportional to N cube. Time period is directly proportional to N cube. Okay, so N initial upon N final. N initial upon N final is N initial upon N final value is 2. Okay, so then you can go back to the options and see which of the when you divide which of the following will give you a value of 2. Option number A had 4 upon 2, which gives a value of 2. So option number A is correct. I hope this made sense to you. Then I'll move to question number 7. Question number 7 says an electron of a stationary hydrogen atom passes from the 5th energy level to the ground level. What is telling you? This is in a hydrogen atom. Okay, in this hydrogen atom, an electron of a stationary hydrogen atom passes from the 5th to ground level. 5th to ground level. Then the velocity of the atom acquired as a result of photo emission will be what? What will be the velocity of the atom they are asking you? Okay, an electron moved from n equal to 5 to n equal to 1. What will be the velocity of the electron which has been emitted? Velocity of the electron which has been emitted. So how will you calculate the velocity? See, again, whatever formulas you know, first you write. See, you know this formula, 1 by lambda is equal to r z square is equal to half 1 by n1 square minus 1 upon n2 square. Okay, so value of 1 by lambda will be equal to r into z square is 1 square. Value of n1 is 1 upon 1 minus value of n2 is, this is our n1, this is our n2. So what happened here was one electron moved from n2 to n1. Okay, so then what will be its velocity? We need to find out. What will be the value of lambda? First you find out. N2 ka square will be 5 square. Okay, so 1 by lambda here will be equal to r into 1 minus 1 by 25, which will be equal to 24 upon 25. 24r upon 25. Okay, then you need to find out what is the velocity of the atom acquired. For the velocity to find out from de Broglie's hypothesis, from de Broglie's hypothesis, what you know is lambda is equal to h upon mv. Yeah, so 1 by lambda will be equal to mv upon h. Okay, and what do you know? 1 by lambda's value is 24r by 25. Can I write that? Can I write that here? Can I write that here? 1 by lambda equal to 24r upon 25. Yeah, So you had to find out what the velocity. So velocity here becomes 24r by 24 into h नीचे 5 m. So v equal to 24 rh upon 25 m. Option number A. Okay, did you understand what I did? They had given you two value of n, then we had to ask what is the velocity. So this is how you find the velocity of the electron which has been emitted. So with this, I'll move to question number 8. Question number 8 says, an alpha nucleus of energy half mv square bombards a heavy nuclear target of JE. See, again, the same question. They had an alpha nucleus which had a kinetic energy of half mv square. Okay, then when it bombarded, it will only have potential energy. It will only have potential energy. Okay, so then the distance potential energy will be what? K into 2E into ZE upon R. I hope you understood this, how it happened. Again, I will tell. Potential energy is equal to K into Q1, Q2 upon R. Q1 value is 2E because it's an alpha nucleus, and Q2 value will be ZD. K 2E into ZD upon R. Yeah. So the distance will be proportional to what? So you equalize because all the kinetic energy is being converted to potential energy. Half mv square will be equal to K 2K ZE square upon R. So R will be equal to K ZE square 4K ZE square upon mv square. So R is proportional to ZE square. R is proportional to 1 upon m. R is proportional to 1 upon v square. So which of the following you think is correct in these options? R is proportional to 1 upon n. Option number C. Okay, guys. So I'll move to question number 9 now. Question number 9 says the transition from a state N3 to N1. This is a state of hydrogen where it is being transitioned from N3 to N1. This is a hydrogen atom and transition of N3 to N1. Okay, and it results in a ultraviolet radiation. Infraradiation will be obtained in which of the following? Okay, this is again from a theoretical question. If a electron is being transited from N3 to N1, which series will it result to? If it is being transited to N1, it will be of Lyman series. It is a Lyman series. And Lyman series always results in UV radiation. This is theoretical question, guys. So please read the theory properly. Again, I'm saying, please read NCERT for this chapter at least properly. Okay. If a electron is coming from any orbit to first orbit, this results in Lyman series. If n is 1. If it is coming to number 2 orbit, it will result in Balmer series. It will result in Balmer series. Okay, and Balmer series results in what? Visible radiation. Remember, they may ask you which of the following series can be a future question. Which of the following results in visible radiation? Visible radiation. That is Balmer series. Then M3 is If n equal to 3, it results in Paschen series. And Paschen series gives infrared radiation. Not only Paschen series, bracket and P-fund series also results in infrared radiation. Bracket mane n equal to 4. When an electron moves from any orbit to n equal to 4, it will result in bracket. If it is moving from 6th, 7th, or 5th to coming back to 4th cell, it will result in bracket. If an electron is coming from 6th, 7th, or 8th orbit to 5th orbit, it will result in P-fund series. All this results in infrared radiation. I hope you understood. So they are asking you, infrared radiation will be obtained in transition of what? If it is being transited to 3, 4, or 5th orbit, it will result in infrared radiation. So in which of the following option they have given you a transition to the third orbit, to the third orbit, to the third orbit in only option number D from 4 to 3. It will result in a Paschen series, and Paschen series in infrared radiation. Okay, guys. So I'll move to question number 10 now. Question number 10 says the wavelength of the first line of the Lyman series for hydrogen atom, the wavelength of the first line means of Lyman series. Lyman mane, the cell is 1, the wavelength of the first line means equal to 2. The wavelength of the electron when it is being transited from n equal to 2 to n equal to 1, n equal to 2 to n equal to 1, this wavelength is equal to that of the second line of the Balmer series of hydrogen atom. Second line of the Balmer. Second line of Balmer. Second line mane, Balmer mane, it will move to n equal to 2. Balmer mane, it will move to n equal to 2. Second cell. Okay. And it is second line. Second line mane, it is moving from the fourth cell. First line mane, it will move from third cell to second cell. It is moving from fourth cell to second cell. So that is, it is second line. It is moving from fourth to second line. And in Lyman series, they have given you first line. Yeah, first line means 2 to 1. You understood this? What is first line and second line? So now they are telling you the wavelength. The wavelength. First, what will be the wavelength here? What's the wavelength here? If the wavelength here is lambda 1 and the wavelength here is lambda 2, what is the wavelength here? R into Z square. Z means 1 square 1. So I'm not writing that. 1 upon 1 minus 1 upon 2 ka square is 4. And here in Balmer series, what will you do? 1 upon lambda 2 is equal to R into 1 upon 2 ka square is 4 minus 1 upon 4 ka square is 16. Okay. So now lambda 1 is equal to lambda 2. They've given you in the question. The wavelength of the first line of the Lyman series is equal to the second line of Balmer series of hydrogen. So lambda 1 equal to lambda 2. So these two equations are equal. These two equations are equal. Equalize these two equations. 1 by lambda 1 is equal to 1 by lambda 2. So 1 by lambda 1 equal to R into 1 minus 1 by 4 is equal to R into the atomic number of, sorry, this was a hydrogen like atom. The wavelength of the first line of the Lyman series for an hydrogen atom. This was an hydrogen atom. This was an hydrogen atom. So this should be 1 square. But the Balmer, for the Balmer series, this was a hydrogen-like atom, something that we don't know. What is the hydrogen-like atom? So RZ square. So RZ square equal to half 1 by 4 minus 1 by 16 will be equal to 16, 4 minus 1. So R cancel. This will be 3 by 4 is equal to Z square into 3 upon 16. Tongue, 4, 3, 3 cancel. So Z square is equal to 4. So Z will be equal to 2. Answer is option number D. Okay, so this was an helium-like atom. The wavelength of the first line of the Lyman series is equal to second line of Balmer series. Z will be equal to 2. I hope you understood. So with this, I will move to question number 11. Question number 11 says, an electron in the hydrogen atom jumps from an excited state N to the grounded state. In hydrogen atom, it moves from excited state N to grounded state 1. The wavelength so emitted illuminates a photosensitive material having a work function 2.75 electron volt. The wavelength which is being emitted here illuminates a photosensitive material having a work function of 2.75 electron volt. If the stopping potential of the photoelectron is 10 V, what will be the value of N here? Okay, so to solve this question, if an electron is coming from N to 1, if its energy is, then its energy will be equal to, if the energy is equal to h upon lambda, this h upon lambda will be equal to what? If energy, the value of energy you know is h upon lambda. So value of total energy h upon lambda will be equal to what? The wavelength so emitted having a work function. Work function is psi is plus psi plus the stopping potential of the photoelectron is psi naught. Okay, the value of psi they have given you 2.75 electron volt plus the value of psi naught they have given you is equal to 10 electron volt. 10 electron volt. So the energy will be equal to 12.75 electron volt. So you need to calculate the value of N. The total energy is 12.75. 12.75. So the value of energy, if you guys know, value of energy is minus 13.6 into Z square N square electron volt. Okay. So the value of this cell, L electron in this cell will be minus 13.6. Value of Z is hydrogen 1. So 1 square upon N square. Okay. And the value of energy of the electron in the first cell will be equal to minus 13.6 electron volt. Electron volt. Okay, so when it is being transited from N to 1, the difference is 12.75. Difference is 12.75. So what can you write? En E1 minus En is equal to 12.75. Okay, when it is moving from N to 1, the energy difference is 12.75. So that's what I wrote here. So now the value of E1 here is minus 13.6 minus the value of En here is minus 13.6 divided by N square is equal to 12.75. Okay, so the value will be equal to if I minus 13.6 plus 13.6 upon n square is equal to 12.75. If I take 13.6 common, it will be equal to 1 minus 1 upon n square is equal to 12.75. Now 1 minus 1 upon n square is equal to, if you take divide 12.75 upon 13.6, you will get 0.9375. 1 upon n square is equal to 0.0625. Value of n square will be equal to 16. So value of n is equal to 4. Did you understand what I did? An electron moved from n to 1, and the total energy given was 12.7. Total energy emitted. So the difference of these two cells will be 12.7. So I subtracted E1 minus En. Then I solved the equation. I got value of n is equal to 4. I hope this question is very clear. I'll move to question number 12. Question number 12 says, out of the following, which one is not a possible energy for a photoelectron to be emitted by hydrogen atom according to Bohr's electric atomic model? According to Bohr's electric atomic model, according to Bohr's atomic model, the value of energy in E1 is equal to minus 13.6 electron volt. In N2, it will be minus 3.4 electron volt. E3, it will be minus 1.51 electron volt. E4, it will be minus 0.85 electron volt. Okay, so the difference between these two is, as you can see here, 10.2 electron volt. Difference between these two will be 12.09. So these are the fixed possible energy emitted, because uh, because electron will not move to any in the space or something. So it has to move from one orbit to another orbit. So when it is moving from 1 to 2, it will emit 12.10.2 electron volt energy. When it will move from 1 to third orbit, it will emit 12.09 electron volt energy. So these are the fixed numbers, fixed number of energy, fixed amount of energy emitted by the hydrogen atom. Okay, it so some values are not possible. Which value is not possible? 11.1. It will never emit a 11.1 electron volt energy, because 11.1 is not at all possible. How can it be possible? 11.1 will be somewhere here, but which is not lying in the orbit. Yeah. So 11.1 energy, it will never emit an energy of 11.1. So the answer here will be option B, 11.1. With this, I'll move to question number 13. Question number 13 says, the energy of a hydrogen atom in ground state is minus 13.6 electron volt. What I told you, for the energy, you remember this formula. For the energy, you remember the formula, minus 13.6 Z square upon N square electron volt. This is the formula for the energy in an orbit for an electron. Okay, you remember all the formula, and do one thing. You can have a paper and write all the important formulas of this chapter in a paper and try revising them every day, so that it will be printed in your mind before the exam. Okay, so energy is equal to minus 13.6 Z square upon N square. The energy of hydrogen atom in the ground state is, so energy of hydrogen in ground state is equal to minus 13.6 electron volt. Okay. So the energy of helium in first excited state, energy of helium in first excited state. For helium, value of Z is 2. First excited state mane N is equal to 2. N is again equal to 2. So the value will be equal to minus 13.6 into Z ka square. Z mane 2 ka square upon N ka square. N is 2. 2 ka square. Tung. So the value will be equal to minus 13.6 electron volt. I hope you understood. Option number A is the correct answer. So now question number 14. Question number 14 says the ground state energy of hydrogen atom is 13.6 electron volt. When its electron is in first excited state, its excitation energy will be equal to what? So again, this question is same. They are asking you what will be the energy of hydrogen in first excited state. So since this is hydrogen, you know Z is equal to what? 1. First excited state mane I told you. In hydrogen, first excited state will be what? N equal to 2. Ground state mane N equal to 0. First excited mane N equal to 1. Like that you go. So the value is will equal to what? You know the formula. Again I'm writing so you remember it better. Minus 13.6 into Z square upon N square electron volt. So minus 13.6 into Z square is 1 upon N square is 4. So minus 13.6 upon 4, which will give the value, as minus 3.4 electron volt. Okay. But what they are asking you in question, they are asking you what is its, this is in first excited state. In ground state, what is its value? Ground state, what is the energy value? 13.6 electron value. Because in ground state, N equal to 1, Z equal to 1. So this will be minus 13.6 electron volt. But this is first excited state, minus 3.4 electron volt. Okay. So they're asking you when its electron is in first excited state, its excitation energy is what? Mane, they're asking you if it wants to if an electron wants to move from ground state to first excited state, what will be the energy required? What will be the energy required? You minus it from here. E2 minus Eg equal to minus 3.4 minus of minus 13.6. So 13.6 minus 3.4 will be equal to 10.2 electron volt. This will be the excitation energy required to move an electron from ground state to the first excited state. I hope you understood. Answer will be 10.2 electron volts. So with this, I'll move to question number 15. Question number 15 says the total energy of an electron in the ground state of a hydrogen. Total energy of an electron in the ground state. Write everything here, ground state, and this is an hydrogen atom. So N equal to 1, Z equal to 1. Total energy is minus 13.6 electron volt. Now they are asking you what will be the kinetic energy of the electron in first excited state. First excited state mein what will be the kinetic energy? So what do you know? Kinetic energy is equal to minus of total energy. So if you know what is the total energy in the first excited state, you know the kinetic energy. So I'll calculate what is the total energy in first excited state. What will be the total energy? Minus 13.6 into z square is 1 upon n square. I'm not writing the formula again because I have told you very nicely before itself. So minus 13.6 upon 4 will be equal to minus 3.4 electron volt. So since you know kinetic energy is negative of total energy, my kinetic energy here will be equal to negative of total energy in the first excited state, negative of minus 3.4 electron volt. So it will be equal to plus 3.4 electron volt. Option number D. Okay. So with this, I'll move to question number 16. Question number 16 says ionization potential of hydrogen atom is 13.6 electron volt. The hydrogen atoms in the ground state are excited by a monochromatic radiation of photon energy 12.1 electron volt. Okay, this is n equal to 1 where the energy is 13.6 electron volt. This is n equal to 2 where the energy is minus 3.4 electron volt. This is n equal to 3 where the energy is minus 1.5 electron volt. Okay, so when you gave an energy of 12.1 to this state, it has minus 13.6 electron volt. Then you gave an energy of 12.1 electron volt. So the total energy here will be minus 1.5 electron volt. So they're saying electron will move from 1 to third orbit. Did you understand? The first I wrote what is the total energy of each orbit. Okay. Then they are saying in the question, that it was in the ground state initially, and then when you gave an energy of 12.1 electron volt, what will happen? Electron will move from 1 to 3. Okay. So now what are the total number of electron spectral lines emitted? For the total number of spectral lines, you know the formula, equal to n into n minus 1 upon 2. What is the value of n here? 3. 3 into 3 minus 1 into 2. 3 minus 1 is 2. 2, 2 cancel. Total number of spectral lines is 3. Answer is option number A, 3. Okay, guys. So with this, I will proceed to today's last question. The total energy of an electron in first excited state is total energy they have given you in the first excited state. Given you is minus 3.4 electron volt. And the kinetic energy in the same state is minus of total energy, which will be equal to plus 3.4 electron volt. This is very simple. So option number A, plus 3.4 electron volt. So, okay, guys, I hope you enjoyed today's session, and I hope I made some of your concepts very clear, which you were finding difficult in. So, with this, the rest of the questions of this today's session, I'll take it in the next session. So, till then, goodbye, study. Well, all the best.